day of linux.conf.au. I'd like to welcome Michael Still to give us a presentation today. Thank you very much, Michael.
Thank you. Thank you. And first of all, thank you all for coming. It's kind of flattering to have people in the room. For those of you who don't know me, my name's Michael. I work on OpenStack, specifically the compute portion, which is called Nova. I'm also the luckiest guy in the world, right? Because Rackspace pays for me to work on my hobby and to hire minions to do the boring bits for me, which is a pretty sweet deal, to be honest. So today's talk isn't about OpenStack. It uses OpenStack as a stage upon which to explain how we added continuous integration of database migrations for Nova. But it's more generic than that. Like, I would like to see other people doing this kind of stuff. And so, it's not really a Nova talk or anything like that. If you're expecting that, I'd recommend you sneak out or something. So what is continuous integration? Continuous integration is the process of every time a human produces a patch set, running automated tests on it to verify that it doesn't break the world. In the OpenStack universe, this means that when you upload a patch set to our review system, we have a system that takes that patch, runs 9,000 unit tests on it, and does a bunch of integration tests as well. So we turn up little test clouds and make sure you can actually boot an instance and the SSH works and networking and stuff like that. But generically it's this concept of things should be tested before you blindly merge them. And that is my only math joke in the whole slide deck. So you've got to laugh, people. That was pathetic, but anyway. Okay. So we've also got to have some terminology. So Nova uses a database ORM called SQL Alchemy. It's basically a library that sits in between the database and our code. And so we can say, an instance is this object. Go persist that in the database. And it knows how to map our object into a series of tables and relationships and all that SQL-y kind of stuff under the hood. And in fact, Nova passes those ORM objects around all over the place. We're only just now deciding that's a terrible idea and replacing them. And it's a lot of work because they're kind of baked in everywhere. A schema version is a particular point in time for the SQL database. So the tables that exist, the columns, their types, the relationships, all of that. In SQL Alchemy land, schema versions are identified by unique integers. It's just an incrementing counter, effectively. And a migration is how you move between these schema versions. So if we're running schema version 100 now, and we upgrade, we'll end up running 101, and we get there by running this thing called a migration. A migration is just a Python function. There's an upgrade function and a downgrade function, but we'll dig into that a little bit more in a second. So what are we trying to achieve? So as I mentioned before, OpenStack is pretty good at unit testing, and in fact, even integration testing with toy clouds. But one of the problems we have is that we don't upgrade real user databases. And we hear from users that upgrading is painful. So a developer might have a really good experience with their code when they've got 10 rows in a database. But when they go to a real site and it's got 30 million rows in that table, then it's all a bit grim. And specifically, this is painful for large public clouds because some of the operations we perform involve an outage window. So if you're changing the type of a column or doing a data format change in a column, then you have to stop the world. And that's not cool for a public cloud. It's possibly okay for an enterprise where you can do it midnight on a Friday or something, I suppose. During this process, we also found some really interesting things. Yes, Stephen?
Do you deal with that in reviews? Like, do you say that this requires an outage and that's not cool? You should add a column or something.
Okay, good question. So the question is, do we deal at review time with this pain? And the answer is kind of, sort of not. It depends on the reviewer. And sometimes it's hard to tell. So this is kind of a specialist field. You have to understand how our database layer works. And the number of people who understand it is relatively small. And generally those people work in that field because they've been punched in the face one too many times by it. So they tend to enter that field in rage, right? And then, if they're asleep when something merges, then, it's kind of, we have this policy that you can't restate migrations once they've merged. So, it can be painful to unroll them and say, no, you really can't do that. So this system is trying to stop a lot of that by having a bot that just says, no, you can't do that, is kind of where we want to go. We found some interesting stuff when we started experimenting with this. We found schema drift. So We found users running Essex and Folsom, which if you don't understand the OpenStack naming scheme is just really old releases from like a couple of years ago, where it wasn't possible to upgrade to our current databases because the models didn't exist. Now these users swear that they never ever tweaked their database by hand. But over time, someone has gone back and changed a model or a migration in a way where these people were just kind of abandoned in an incompatible universe. So that's a kind of a big deal. It is not acceptable. And we need ways of detecting that sort of thing. We obviously found performance issues because that's what we were aiming for. There are examples of migrations that rewrite data where it would involve a couple of hour downtime window, and that's just not okay. And we also found a bunch of broken downgrades. So I said before that a migration has an upgrade method and a downgrade method. Developers obviously think more about the upgrade because that's the bit they want. And so often there's a downgrade, but sometimes these downgrades don't work. And in fact, I can think of examples where they deliberately don't work. For example, you did a data format change and it's a lossy change and you threw away the original data. So you just can never get it back. Right? Maybe you could recalculate it, but maybe that's really slow. And I personally think that downgrades are kind of important. So, to take a little tangent for a second, this is kind of open to debate at the moment. You're a cloud, right? And you go to do an upgrade. And then sometime later, you discover you deeply regret the upgrade. There's a bug, it's subtle, it took you a couple of days to find it. Users have performed operations in the database. The state has changed. So you can't just restore from backup. What do you do? I think the answer is you probably run the downgrades to something you know you trust, because the database has to match the version of the code you're running because of these model objects. But that can be really painful too, because the downgrades don't necessarily work properly. Yes, and the point from the audience is if you've done a lossy transformation, it may not be possible. So this is still open to debate inside the OpenStack dev team. For example, at one point we said, if you're doing a lossy transformation, you must stash a copy of the original data in the database so that we can go backwards. And that's expensive too, because you're copying data around.
It doesn't help with the new user data. The new user data doesn't have old data to transform to. You're completely screwed if you've done new user data.
No, okay, yeah, so the point is even if you take a backup, that doesn't help say instances that were created since you did the upgrade and before you regretted it. So this is a complicated problem, and I think the point I'm trying to make is we don't have a good answer here, but we have bigger, more horribler problems, and we'll get to this one later. It's kind of where I'm trying to go. The other thing I should say is I want to be really clear about who did this work because I'm not a terrible human being. One of the problems with LCA is you propose your talk 9 months before you give it, so it's hard to predict what's going to happen. So I wrote the prototype implementation of this system, and then a couple of months later we hired Josh Hesketh, and this was also his starter project. So he actually, it's embarrassing. I said, productionize this, and what he did was he looked at it and said, you are a terrible programmer, and threw most of it out. And wrote something that's much, much better. But so a lot of the code was written by Josh, right? And so I helped him, get that into production. I fixed bugs and stuff, but this is complicated. I'm not the sole author of this work, is what I'm trying to say. But if you find any bugs, it's Josh's fault. And I should also say, whilst this isn't a marketing talk, this work was all funded by Rackspace, and they're very nice, and they have lovely hair. So before I can really talk about this, I have to give you the 10-second overview of how we do code review and continuous integration in OpenStack land. I am cognizant that there's been a few talks about this already, so I'm going to go really quickly and hopefully confuse you so you don't ask questions. A human writes code. They upload it to our code review system with a tool we wrote called Git Review. It ends up in this. This is Gerrit, our code review dashboard, which is an open source project written mostly by Google, I think. You can see at the top, these are my code reviews, the code I've written that I want to get merged. And at the bottom is, Gerrit trying to guess what I should review. But that's not relevant to the talk, so ignore it. In the V column over there, you can see a -1. This means an automated system decided my code wasn't up to scratch. So V for verified, by the way. Specifically, in this case, I think I had a PEP8 failure. There was, a style lint failure or something. But these things happen all the time. The R column is for human reviewers. So here is a case of a human saying that he or she doesn't like my code and it shouldn't merge yet. Eventually, once you get them drunk enough, the humans agree with you. And then you get a +2. Now, +2 must come from a core reviewer, so there's a subset of the review team that can approve things to merge. And we have a rule that you need 2 of those people to approve before something merges. So this is the first approval. And then later on they say yes, may, a second human comes along and says yes, may merge. Now that's interesting because what happened was that code then failed to merge. Now in this case it was probably a failed rebase, so the code had moved underneath me, and so I have to come in as a human and use my thinking brain to get it to merge because the bot failed to. But this could also be someone landed code that makes your code not work in the time it took for the review to happen. And that's all I'm really going to say about Garrett. So the bots we have at the moment that do this voting, how are they implemented? So the humanoid writes code. They send it to Gerrit. There's a Zool run by the OpenStack infrastructure team. Its basic job is to read a feed of things happening in Gerrit and turn them into test jobs. So it talks to a pool of Jenkinses. There's 5 of them at the moment, I believe. And the Jenkinses own a pool of test virtual machines they run tests on. We have a rule that you only ever use a virtual machine once for testing, and then we throw it away. Because some of our tests do things like, twiddle the state of libvirt, so the hypervisor state. And so it's just easier to guarantee we're at a clean state at the beginning by throwing things away. I say there's all because it's run by the OpenStack infrastructure team. The stuff we've done is not run by the OpenStack infrastructure team. So our system is very similar. So this includes their system. I know the scale of the picture changed slightly, but we run our own private Zool. It's the same code base, and the only reason it's separate is we didn't think it was fair for the infra guys to have to manage our stuff while we were still stabilizing it. We could totally merge them together later. It just involves, some sort of mutual level of confidence that this wouldn't be horrible for them. Our Zool doesn't like Jenkins because, Java. So we wrote a thing called Turbo Hipster. Turbo Hipster is a Zool job runner. So effectively what it does is it starts up a Python binary, it connects to Zool using Gearman, it waits for jobs, it executes them, it returns results. Turbo Hipster has a series of task plugins, and that's where you do your local testing logic. So when we implemented this database migration stuff, what we actually did is write a task plugin, ignoring the fact that we had to write Turbo Hipster first. The task plugins store logs, which get pushed to a log server, and then at the end of the test run, the task plugin says to Turbo Hipster, I'm done, and it kind of all routes back. I know the arrow fibs because it goes straight to Gerrit, but it routes back up the stack and says, here's the vote, here is a text description of why I'm voting that way, and off it goes. And those text descriptions include URLs to the logs of the test run. Now that's an important point. OpenStack would call this a third-party test system because it's not run by the infrastructure team. And one of the things we've learnt in the last few weeks is it's important to give developers logs that explain why the test failed. It's not really fair to have a machine say no to someone but not tell them why. The developer can go read the logs, work out what's wrong, fix it, or at least to triage it and say, I don't think this is a problem in my code, and come back and kick you until you fix the test system. So, it's obvious in hindsight, but public logging is good, or logging accessible to the developers at least. And to give you an idea of the scale, in Nova we have about 163 unique humans for the current release, proposing patches. They're proposing about 100 patches a day. We run about 20 Turbo Hipsters that happily keeps up with that workload, and each time a patch is proposed, we run 8 tests. So we're running about 8 database migrations per patch set per day, if that makes sense. So far, we've run about 25,000 database migrations, and we're not talking significant amounts of data for the logging. It's only 1.5 gig. So let's talk about Turbo Hipster. So Turbo Hipster, of course, means it's testing ironically, which we thought was a hilarious name because most of the infra team are hipsters, but apparently it's less hilarious to them. I'm thinking Monty here. So Turbo Hipster is a test runner. So these task plugins register things they can do. Turbo Hipster reports those to Zool. Zool has a config file that says, for this event, execute this thing in this queue that implies these tests effectively. You can have more than one queue, although the reality is we only have one at the moment. Just run a check, basically. So yes, you register with Zool. Task plugins are run when they're requested. The logs are stored and you return results. It's kind of not that complicated. And the actual voting in Gerrit is handled by Zool. You just send a data packet back that says, hey man, do this thing. And this is what a vote looks like the text comment. So the blue things are obviously links, hopefully obviously, and then success or failure. And with the failure, you can give a helpful message. So, hey, this migration took too long, or whatever. You'll notice that some of our tests are non-voting the last 2 lines. That means we're not confident yet that this thing isn't returning false positives. Specifically in that case, the user2 data set required a stable backport to happen first, and that stable backport took a really long time to happen. They actually pass now. So the task plugin, they're really not that complicated. So it's just yet another Python plugin. Basically, you only have to implement 2, maybe 3 of those methods, and the others are helpers, but I think everybody will have those helpers. So when you initialize, you of course stash a copy of your configuration, but you also have to define how many steps you have in your task. And that's important because Zool presents a dashboard to users that has a little progress bar of the testing. And so if you have more than 1 step, the progress bar is not just all or nothing. Stopping a worker is relatively boring. And then this is where the work actually happens. This is starting a job. So you send a data packet to Zool saying, hey man, I'm starting the job. You start walking through your steps. Each time you do a step, you increment and say, hey Zool, another step is being performed. And then at the end, you send some results. And these are helpers that I think are probably generically useful. So, getting information about the job, sending a packet that says, hey man, this is what I'm doing, and incrementing a step, which is, not super complicated either. Yes?
I forgot to tell you, on the plane, I refactored it all, and you now only need the start job.
I don't love you anymore, Josh. So it's performance review season at Rackspace. And Josh is telling me that he's refactored all of this, so this is wrong while on the airplane on the way over here. But his code hasn't merged yet, so this is still true.
It's now easier, is what I meant.
Okay, I think the point we're trying to make is that it was not very hard before and it's easier now. It's awesome, man. So the database upgrade script is actually a bit of an anticlimax after all of those fun, hipster mocking names. It's basically a Python script that runs a shell script. And so we've expressed all of the upgrade logic in shell. So the upgrade script is handed a copy of the Git repository. It has the patch under test in a branch. So the first thing we do is we check out master, and we have a look at the database we're testing, and we say, what version are you? If it's a stable release, like say hypothetically a database from Folsom, what we'll do is we'll check out the stable code associated with the next release, so Grizzly, and we'll run those upgrades. And then we'll run the next stable release, so Havana, and then, because at the moment we're doing the I release, Icehouse, we'd then jump to master and run those upgrades. And so finally we have a user database that's in a reasonable starting state. And the reason we go through all of those again is because we want to detect whether or not we can still upgrade from relatively ancient releases. Like in OpenStack land, Folsom, so 3 releases ago, is considered very, very old. Friends don't let friends run Folsom. And then, so we apply the upgrades from master, so we have something in a reasonable starting state, and then we apply the changes from the patch set. So we test the upgrade. If that works, we then downgrade down to the start of master again, and then we run through them all again. So what we're effectively doing is testing that one upgrade works, but then downgrades all the way to the start of the release work, and then upgrading back again. And we do that because we found problems with, say, foreign key constraints. So we're just testing whether or not we're clobbering the schema when we do a downgrade or an upgrade. And then we pass or fail, and we return logs. The way the logs happen is relatively interesting. So the shell script just returns an exit code. And so if you have something really bad happen, like, pip installing packages failed, the task plugin detects that the exit code is wrong and will say, oh my God, I didn't even run the tests, man. It all went horribly wrong. For most cases, what we do is we just write a log to disk and then we do text analysis of that log to determine if the test passed. So, we go through the log and we can calculate how long each migration step took and what the end schema number was and stuff like that. So, for example, with the case where the patch set has a broken upgrade but for some reason doesn't return an error code, we can tell that it ran, but that we didn't end up in the expected destination state, and therefore it's still a fail. And it took a little bit of fiddling to get the script running, but I think that's mostly because OpenStack is a bit complicated. It's not conceptually difficult to write a script to do this. In fact, if people had a test they could express as a shell script, we could do the rest of the glue in a couple of hours, I think. It's not hard anymore. But that's kind of the point. We were trying to make this easy. So, I think we have achieved a reasonable goal here. And in fact, we could go mad with plugins now, right? So, it feels a bit to me like everything should be a plugin. So Zool is this system that handles things triggered by events in Gerrit. And then, these tasks don't even have to be tests. It could be, hey, I've noticed that the primary author of this file hasn't been, a carbon copy to a code review from someone who's changing it. Maybe we should just do that. Or, maybe you're particularly interested in a block of code, so you could subscribe to it or whatever. A lot of this stuff Gerrit supports, but I think ad hoc scripts give us a bit of flexibility that might one day be interesting. Another good example is, dependent patches, for example. We have a repository that is all the pip requirements for OpenStack, and so people, if they want to change the version of the library we're running, change it there, and then it kind of flows down to the other repositories. And so we could automate that kind of stuff. I should say, of course, that all of that stuff is all already automated, but it's done with Gerrit triggers. And it's not clear to me why we still need Gerrit triggers. I feel like we could put all of this in one system and it would be easier for the developers to understand because they wouldn't need to know how Puppet works, for example. Because at the moment, a bunch of this stuff is deployed with Puppet. I might be wrong, I don't manage these systems, and maybe this is also because this is my new toy and therefore cool. Now, security is hard with database migrations specifically, although maybe that's true of all unit testing. Effectively, what we're doing is we're taking code from third parties we don't necessarily know much about, and we're running it. Now, in our case, it's worse, right? We're running it on data we think is special and that we don't want everyone to have. So hypothetically, this might be the production database for a public cloud. And I don't really want you to know how many instances are running in, say, the Rackspace public cloud. I don't want you to know who our biggest customer is, or how many virtual machines they have, or what features of our cloud they use. So we have to be a little bit worried about leaking that data. And I should say, before you start actively attacking this system, we're actually not using the Rackspace database yet, because we're still addressing some of these questions. But certainly the intention is to start testing against production databases, certainly the Rackspace database. And then the next step is we're going to go and sweet talk people like HP into letting us test with their production databases. So one of the reasons the system's built like this is that we don't have to run all the workers. So we can run the Zool, and we can let you run workers in your data center with your database that we never see and never touch. And all you come back with is logs and a yes or a no. And that's cool, because it means, we're not asking people to tell us things that are possibly quite proprietary in order to get a reasonable experience out of an upgrade. So we do some stuff to try and mitigate this. The workers, so how could you attack this? The migrations could write interesting information to disk on the worker. So the workers only run one network service, SSH. Everything else is, Turbo Hipster is talking over the network, but it's initiated by the worker. So, you could do that, but the set of people who can log into the machine and look at the disk is limited. You could write statistics to the logs, right? So, we return the log that the database migration wrote, and so you could just write stuff there. So we actually run the logs through a simple anonymizer before we return them. We try and detect cases where a log message doesn't look like a log message should, and then don't return those. So we filter. I will be honest and say we filter the logs, and maybe one day that will bite us. And we're also working on dataset anonymization, but to be honest, that was a harder problem than we realized it was at the start, and so we have chosen to ship without it, just to get the ball rolling, and we will go back and focus on that more. And the other thing we do, right, so you could, in your upgrade code, open a TCP connection and just stream our database out, right? So we run the testing processes without network connectivity. Now, this is actually interesting, right? We need network connectivity on the workers because they talk to Zool over the network, obviously, but also because we have to download a whole bunch of pip dependencies and stuff because the patch set might change the dependencies. So we want to specifically run the upgrade step with no with no network access. So we started off by looking at Linux containers. Now this was hard. It wasn't hard because of containers. It's hard because of Python virtual environments and stuff like that. We had a lot of trouble making virtual environments reliable where you build them on outside the container and then want to use them inside the container. You can make the virtual environment relocatable, but when you go and actually read the documentation, relocatable virtual environments aren't meant to work. It was an experimental feature, it never worked properly, and it certainly didn't work for us. So we went off on this weird tangent where we tried to make containers work, and it made us sad. So we came back and thought, well, what can we do instead? Now, it turns out modern Linux kernels have this cool feature called network namespaces. So what you can do is you can say, I want an entire a second network stack on my machine, and I want this process to run in that separate network stack. So hypothetically, if you had a process where you wanted it to use a different default route or a different link or something, you can just bring up a different network stack with different routing rules and off you go. Like, there's other ways of doing this in the Linux kernel. Tagging is an obvious option, but network namespaces make it really easy. And this is how we build the network namespace. So first we create a namespace called nonet, and then we create a vth tunnel between that namespace and the default namespace on the machine. So vth0 is in the default namespace and has a RFC 1918 private IP, and then nonet has the other end of the tunnel with another one of these IPs. And then what else do we do here? We do some relatively simple IP table stuff to just make sure that we can talk to MySQL for the testing, but people on the internet can't or whatever. And so basically what you end up with is our database upgrade process talks to this new network namespace, and the only thing the new network namespace knows to do is talk back to the default namespace to get to MySQL. There's no...
One of those V0s, V1?
Yes, okay, it's true. Sorry, so that's vth1, and this is vth0. So yeah, the only thing that the nonet namespace knows how to do is to get back to the default namespace to talk to MySQL. And we tested this and stuff, so it's pretty cool. And it's a lot simpler than containers. I'm pretty happy with how this works. And I can think of lots of other bonkers things you could do with this sort of facility in the kernel. And then you just say, hey man, run my binary in this other namespace, please, and off you go. So I promised to talk about some interesting bugs we'd found. So there's a few of them. I kind of want to talk about two, but that's mostly because, we could go on forever. So the first one is a classic example of something we were actually looking for. So a developer wrote an upgrade. On his trivial system, it was relatively fast. It took seconds to run. But this was a data format conversion of the contents of a column. So what he did is he did a select, and then he iterated through the rows in Python, did the conversion, and wrote it back to the database a row at a time. And it worked, and it passed all the other tests, right? And in fact merged. Reviewers said, looks like code to me, job done. On our test database with 30 million instances, which I don't think is a particularly large database, especially when you take into account that those instances can be deleted, so it's not 30 million running instances, it took about 20 minutes to run. So not cool. Especially when, if you're doing an upgrade from a stable release to a stable release, you're stacking up a bunch of these upgrades, right? You might run 40 of them instead of one. So this was actually a really interesting experience. This is the email I sent to him. And I said, this is not cool. And so he said, yeah, fair enough, you got a point. And he was really helpful, all credit. And so he started tweaking his review. And so he'd go back and he'd upload a patch set that was slightly different. And then he'd wait for the test system to run and return results. And he'd be like, ooh, close, but not there yet. And he iterated. And we were asleep. And he went through like 12 versions of the code, progressively getting better. It was really fun to watch him interact with the system and come up with better code without anybody having to help him. He never had access to the database. And in the end, he got this down to being a sub-second migration because he just expressed all the data conversion in SQL. And then the SQL engine, which is really good at churning through data, churned through the data. So that was cool. And if you want to see the difference between the two versions of the code, that's a link. But you can grab that from the slide deck later or something. And this is a really recent example. This is from last week. So I have to kind of explain the feature. When you boot a virtual machine, you need metadata to configure the virtual machine. And let's say hypothetically that your virtual machine's operating system is a little bit stupid. And it can't do DHCP or whatever. So for some users, we need to present them with the configuration information on a virtual hard disk so that they can configure themselves, bring up the network, and then be a useful computer. I guess, hypothetically, I can also imagine cases where maybe not all the virtual machines in your cloud need networking, right? Because you have console access separately. So maybe sometimes you don't want networking at all anyway. Now, back in the day, we would let you specify an image from the image store. We would stream it, apply the metadata to it, and then hand it to you as your configuration option. It turns out this is stupid and horrifically insecure, and we couldn't think of a way to make it secure, basically. So we said, we're not going to do that anymore. And so instead, what we do now is we generate it's actually a ISO 9660 image hard disky thing from scratch, and then attach that to your virtual machine. But the APIs still expected for an image ID to be passed through. So what we did, because we're mature adults, is we said, let's do something horrible. So in the API, if you specify any non-empty string, what you're saying is create me a new hard disk and attach it to my virtual machine. And that was compatible with the old API. We didn't have to change clients and stuff. But it had this weird side effect where effectively we're treating a varchar column in the database as a Boolean. And I can see that that's not perfect. And someone filed a bug, and then a developer, a well-meaning developer, came along and said, that's horrible. And so he changed the format of that column to a Boolean. That you can't do that. For a production database, that might take tens of minutes to execute because it's got to throw away that column. It's got to rewrite the table, in fact, in MySQL. Yeah, sometimes adding a column can be an online operation, but changing the data type of a column is not. I'm being told Postgres either. So it's super horrible. So I think it is in MySQL too. So we're asserting that it's probably a full table lock in both engines as well. I think it's a stop the world operation, to be honest. So it meant we could go back and say, no, really, you can't do this, right? We agree this is horrible, but ignoring the fact that we have this API compatibility problem, luckily we're about to throw that API version away and maybe we could do something less horrible. You can't just rewrite this table. And I think the reality is, in fact, there's no reason for it to even be in this table anymore. You put it in, we've got this metadata table that's interesting facts about an instance, we just chuck it there. So this was kind of probably the wrong approach anyway. But it's cool because now we're actually catching these things before they merge. And as I said before, we kind of have this policy of not restating migrations once they've landed because we have people doing continuous deployment. So, Rackspace, for instance, there's a reasonable chance we've applied the migration if you've merged it, even though there hasn't been a release yet. So, if it takes us a couple of days to catch a problem, then what do we do? Unless we make the migrations idempotent, which isn't always possible. So catching these things really early is really important. And yeah, so I'm happy that we caught this. I might have gotten a little gloaty on an internal mailing list. There's some interesting secondary effects as well. Because we run every migration chain the whole way through, we actually have a lot of data about how long each migration step takes, specifically for a certain instance type in the Rackspace cloud. But ignoring that, we know how long these things should take and what they look like now. To the extent where we set a maximum time for each migration step, and we do that by doing a statistical analysis of the times it's taken previously and trying to guesstimate what is a reasonable time. I did statistics at uni 15 years ago, so I am not confident that our methodology isn't bogus. But what we do at the moment is we take the mean, add 2 standard deviations and go, close enough. It turns out that might be entirely not a good enough approach anyway, because it turns out the I/O bandwidth on these instances is variable. Because we use relatively small instance sizes, we share with a bunch of them on a machine, and so the bandwidth can be unpredictable. So what we do now is we do an I/O performance test at the start of the test run, and then we moderate the times migrations take by the I/O performance we believe we are experiencing. And that still might not be good enough, because I did a statistical analysis of that just before I came to the conference, and that was actually worse at guessing what was an acceptable number than just blindly trusting it. Mostly because the data set was much smaller, I think, because we'd only had a few hundred test runs versus 7,000 or 8,000. It turns out that MySQL has performance counters that might mean that we don't have to care about wall time at all, but I have to trick Stuart Smith into sitting down with me for a while and explaining performance schema, because it's relatively new and we're not sure if it gives us the data we need. But it would be nice to not worry about wall time and to use a first order metric, not a second order metric, effectively. So there are some flaws in this system, and it's not perfect. We're also learning as a community how we bed systems like this down. We know this is giving false positive votes at the moment. So Josh and I are reading every single vote. And if it's lying, they're walking in and saying, we're so sorry, we've identified this bug from this thing, we're working on the bug, but we fixed the incorrect vote for now too. Whereas there's another third-party test system that came along recently and just gave a whole bunch of negative votes and then bravely ran away. And so there's some social questions about how you do this stuff as well. We also have a lot of data about the comparative performance of Percona versus MySQL, the two engines we use at the moment. Percona is about 10% faster, as best as I can tell. And less jittery, like the latency, the time the migrations take varies less than it does with MySQL. Sometimes it's just really slow in MySQL. So that's interesting. It would be interesting to add, say, Postgres, and there's people working on DB2 and stuff, to a system like this and say which database engine actually does the best for us.
In terms of migration or anything?
This is only measuring migration times. So it's true, that's not a particularly common operation, but it's a very painful operation. Yeah. I actually personally think that maybe we shouldn't be using SQL databases at all. But we need to get away from having ORM objects all over the code base before we can talk about doing anything else. So where to from here? So everything feels like a Turbo Hipster plugin to me now. And I think Turbo Hipster is a generically useful tool at the moment, specifically if you're using Zool. But I don't think it would be that hard to write a Zool plugin that, say, used GitHub pull requests instead of Gerrit, for example. No one's done that work, I don't think. But Zool is probably more generically useful than people realize as well. And we have baseline performance metrics for a bunch of instance types. So Rackspace is a little bit unusual. We run our production databases for public cloud in instances on the cloud. It's actually we have a separate management cloud. But we run virtualized database servers. And so this has a direct correlation to how a production performance would feel. So that's kind of interesting too. And I've run out of slides. So do we have any questions? Yes?
Is Turbo Hipster open source?
The question is Turbo Hipster open source. So I probably should have been clearer about this. LCA actually has a policy that everything you talk about has to be open source. My team only does open source. So this is on GitHub. Well, it started on GitHub. It's now in StackForge. It's Apache 2. We would actually really like contributions from other companies. That would be cool, because then it wouldn't be all our fault. We had to build a bunch of other tools along the way, or are building other tools. So the log, pretty print log server system is called Laughing Spice, and it's, I think, only in GitHub at the moment. The database anonymization tool is called Fuzzy Happiness, and we're still working on it, but we'd love help from people smarter than us. But yes, so it's all open source. Yes?
So you said that you don't want migrations to change once they've landed. I thought you said earlier that 186 change had landed, even though the guy went back and did like 12 iterations while you guys were asleep.
Right. Yes, so the blanket policy in OpenStackistan is that database migrations don't change. We violate that policy occasionally when we think we can get away with it. So specifically because we caught it very quickly and like the restated migration happened within a day or two, we decided it was okay. We generally know who's doing continuous deployment, so we can give them a heads up and say, don't deploy. Just, hit the big red button, we've made a mistake, we're going to fix it, we'll get back to you. But, for example, we couldn't revert the patch, because if someone had deployed it, their models would no longer match their database and smoke would come out.
Wasn't the fix to that the same operation anyway, just a lot more efficient?
The fix to that specific problem was restating the operation as a SQL operation. So yes, I think the data ended up looking the same at the end. It just wasn't so horrifically inefficient in the transition process.
Don't go through Python.
Yeah, it turns out database engines are good at data, right? So, although, man, Mongo would be awesome because it's web scale. So, I think we should move to Mongo.
I had $1 for every time I've seen someone select star from a table, transform it in their application, push it back down.
It works really well on trivial test systems with 10 rows in the table.
It doesn't work well.
But yes, so basically the whole point is we're trying to make upgrades a less horrible experience for users, right? I think ultimately, like OpenStack's in this interesting space, right? Generally, the people we're talking to are deployers, not end users. And if those guys have a really bad time, they'll just go elsewhere. So we only have a limited window to get this right, I think, before we're voted off the island. Anything else?
Still got 5 minutes.
I've got 5 minutes. Oh, I talk faster than in my practice, apparently.
Talk a little bit about the consistency of this, timing of this, about how long does it take before all these tests to run?
Okay.
I can conceivably look it up myself and find out how fast the thing votes when after a patch comes in, but typically, how long is it between a patch going through starting to get review and your system picking it up, testing it, and retrieving its vote?
So the question is basically how fast are we? But there's some nuances to the how fast. So the latency between you uploading a patch and us starting testing it is in the order of seconds. It depends if we have idle workers. So when we get towards release time, we'll probably have to grow the worker pool in order to keep that latency low. It takes us about 15 minutes to upgrade a 30 million row or 30 million instance database from Folsom to trunk, which isn't too bad, especially given it's on a not very large virtual machine, right?
That's plenty fast. No patches can pick up 2+2s and vote unless that.
Yeah, we take about a third of the time of Jenkins, right? So it's actually kind of fun because often we'll fail before Jenkins fails about something that's obviously a failure. You've got a typo. It's just never going to run, right? Maybe it passes PEP 8, but it's wrong. And so I personally like the idea of failing fast. Clark and I have disagreed about this week. It turns out that we tried it once and people didn't like it, but those people were clearly wrong. We don't have performance instances in the Sydney Rackspace cloud yet. For non-Rackspace customers, we recently shipped this new kind of compute node called a performance, which runs instances called performance instances. So everything's on SSD instead of spinning Rust, for example. So I think we'd see much better performance out of those. That's certainly what the data from other people says, but we don't have them in Sydney yet, and we run all of this in Sydney because those computers have a cool accent. So, we could pick up the whole thing and move it to Texas or something. That would be relatively trivial, but I don't see the point. We're just going to hold our breaths for however long it takes.
Faster than the Jenkins chapter things. You don't need to go faster than that.
Yeah, and the thing is, like, how long's a piece of string, right? It actually doesn't matter how long the migration steps take, as long as we have a meaningful line in the sand for what's too long, right? We could run these on a 486, as long as we know where to draw the line. So, yeah.
Do you run migrations against Postgres, or do you just say Postgres?
Do we run migrations against Postgres? Do I hate Postgres? So there's two questions there, and you've nearly hit your quota. We do not run migrations against Postgres, mostly because no one runs Postgres in production, as best as I can tell. Hypothetically, if we wanted to run against Postgres, we would have to take a MySQL database and convert a dump to something Postgres compatible, load it, and then run that. And we'd have to answer questions about, did this migration fail because our method of converting between engines was flawed? Right? I'm not aware of anybody using Postgres for MySQL in production. Do I hate Postgres? Well, why, yes, I do.
Nova rather than you specifically.
So Postgres is supported by Nova. Or does Nova hate Oh my God, there's so many questions here. Nova supports any database engine that SQL Alchemy supports. So SQLite, MySQL, Postgres are the obvious ones, given that Percona is a subset of MySQL, effectively. I'm not aware of anybody running Postgres in production, mostly for historical reasons, and also because it doesn't work, or didn't work last time I looked. So
yes, we've just tried that recently, and there's still issues.
I am assured it still doesn't work. So the problem is there are subtleties that SQL Alchemy is leaking through. Data types, I think, is an obvious choice, right? So the Postgres data type for an IP address is not the string that we use in MySQL. Kind of. Oh, don't be a hater, man. It's clear to me that MySQL is better, and I'm not listening. So yeah, it's a known issue, right? And this is one of the ways we would fix that is by saying, sure, Postgres works on these trivial databases. We run Postgres tests with DevStack now, and they pass, but not real production databases. So clearly we need something like this, right? There's also a team at IBM working on DB2 support. And I would think you couldn't possibly ship that without doing something like this as well, because you'll have exactly the same problems.
Right. The Postgres community is more than welcome to stand up Azul just like this.
I would.
The Postgres community is more than welcome to stand up a bug tracker and CI system first.
I would go further. If the Postgres community or someone who wanted to run Postgres in production came to me and said, I will help you do the database migration, because every time I use Postgres, I have to work out how to do show tables again. If someone wanted to come and give us a hand, we would run it on our boxes. I would provide the compute resources. I'd be totally happy to do that. I just need someone with expertise and someone who'd say yes, and then I'll go and fix all those bugs. Because, ew, Postgres, I'm not doing it.
I could probably hand you HP compute resources too at the same time for that.
Cool. I think we will declare that time, yes?
Thank you very much. Can we please thank Michael again for the talk?